What would happen if the sharpest scientific mind of the 17th century woke up today and discovered that machines can now think? What would Blaise Pascal do if he opened his eyes in 2025 and found that the very concept of computation he pioneered in 1642 had evolved into systems capable of modeling quantum fields, predicting protein folding, and simulating the birth of galaxies in a matter of hours? The question is not merely philosophical. It is deeply practical, because Pascal was not a man who observed the world from a distance. He was a man who built instruments, ran experiments, climbed mountains carrying barometers, and refused to accept any assumption that had not been tested against reality. And reality, in modern physics, has become stranger and more beautiful than anything the 17th century could have imagined. Let us start with what Pascal actually understood about the physical world, because it matters enormously. In 1648, Pascal organized the Puy de Dôme experiment, sending his brother-in-law Florent Perrier to the summit of a dormant volcano in central France carrying a mercury barometer. The column of mercury dropped by more than 3 centimeters between the base and the summit, a difference of roughly 85 millimeters of mercury over an altitude gain of approximately 1,000 meters. This was not a minor observation. This was experimental proof that the atmosphere has weight, that pressure is not uniform, and that what appears invisible is in fact measurable. Pascal's genius was not just theoretical. It was his absolute insistence on turning an invisible force into a number you could read off a glass tube. That same instinct, the instinct to make the invisible, legible, and quantifiable, is exactly what modern AI is doing for physics right now. Consider quantum mechanics, the domain where modern physics most desperately needed a new kind of tool. The Schrödinger equation, formulated in 1926, describes how quantum systems evolve over time. The mathematics is elegant, the problem is computational. A quantum system with just 50 interacting particles requires a state vector with 2 to the power of 50 components to describe it completely. That number exceeds 1 quadrillion. No classical computer, no human mathematician, and no team of physicists working for 1,000 years could solve that system directly. For decades, physicists used approximations, perturbation theory, density functional theory, variational methods, each one a brilliant workaround for a problem that was fundamentally unsolvable by brute force. Then neural networks entered the picture. In 2019, a deep learning architecture called FermiNet, developed at DeepMind, learned to represent the quantum wave functions of electrons in atoms and molecules with an accuracy that surpassed most traditional quantum chemistry methods. It did not follow the textbook equations step by step. It learned the underlying structure of quantum states by training on known solutions and then generalized to problems that had never been solved before. This is precisely what Pascal would have recognized as the right approach. When you cannot compute something directly, you build a machine that captures the pattern. He built the Pascalina, 50 physical gears encoding the carry operation of arithmetic. FermiNet is 50 layers of matrix multiplications encoding the antisymmetry of fermionic wave functions. The logic is identical, the scale is incomprehensible, but the connection goes even deeper when you look at Pascal's work on probability. In 1654, Pascal and Pierre de Fermat exchanged a series of letters that founded the mathematical theory of probability. The core problem they solved, known as the problem of points, asked how to fairly divide the stakes of an interrupted game based on each player's chances of winning if the game had continued. The solution required reasoning not about what had happened, but about the full distribution of what could happen. This is exactly the mathematical foundation underneath modern AI. Every large language model, every physics simulation network, every protein structure predictor is operating on probability distributions. When AlphaFold 2 predicts the three-dimensional structure of a protein, it is not finding the one correct answer and returning it. It is sampling from a probability distribution over possible structures, weighted by learned physical constraints, and returning the most probable configuration. Pascal would not have been surprised by this. He would have understood it immediately. He would also have immediately questioned the calibration of the probability estimates, because that was who he was. There is one area where Pascal's collision with modern physics and AI becomes almost unsettling in its implications, and that is the simulation of complex systems. One of the most profound open problems in physics today is turbulence. The Navier-Stokes equations, which describe the flow of fluids, are deterministic in principle but chaotic in practice. A tiny change in initial conditions produces wildly different outcomes after a short time. Meteorologists, aerospace engineers, and plasma physicists have all wrestled with this for over a century. In 2022, a team at Google Brain published results showing that a neural operator architecture trained on datasets of fluid simulations could predict turbulent flows at speeds 1,000 times faster than traditional numerical solvers while maintaining comparable accuracy. 1,000 times faster. For Pascal, who proved in the 1650s that atmospheric pressure follows predictable mathematical laws even across altitude, the idea that a trained network could predict the chaotic behavior of a fluid would represent the completion of a project he started. He measured the atmosphere. AI is now predicting how that atmosphere moves. Pause here for a moment, because something important just landed. Did you feel the weight of what that means? If you have ever looked at your own life and felt like a system too complex to understand, too chaotic to predict, too full of variables to control, I want you to know that you are not imagining the complexity. It is real, and you are not alone in feeling overwhelmed by it. Drop a comment right now with exactly where you are. You can write, "I want to understand the invisible forces," and just that phrase will connect you to thousands of people watching this who feel exactly the same pressure you feel. Your words matter here. Now, let us go even further into what Pascal would actually build. If you are finding this kind of content genuinely useful, the kind that takes science seriously and asks real questions about what it means for how we understand existence, consider subscribing. Every week, this channel brings the same depth and rigor to questions that most people either oversimplify or avoid entirely. You will not find empty inspiration here. You will find real ideas that change how you think. Subscribing takes 2 seconds, and it means you will not miss what is coming next. Now, the hardest question. Would Pascal have trusted AI? The answer, based on his actual scientific practice, is a conditional yes with a rigorous asterisk. Pascal was deeply suspicious of any reasoning that could not be grounded in experiment. His famous disagreement with Descartes over the nature of the vacuum was not merely philosophical, it was methodological. Descartes believed a vacuum was philosophically impossible and therefore must not exist. Pascal ran the experiment and showed that it did exist, period. His epistemology was empirical, before the word empiricism had the weight it carries today. This means Pascal would have accepted AI-generated physics predictions exactly as far as they were verified by experiment and not 1 millimeter further. He would have been fascinated by the fact that neural networks trained on quantum chemistry data can predict molecular energies to within chemical accuracy, a precision of roughly 1 kilocalorie per mole. He would have been thrilled. And then he would have immediately asked what happens at the boundary of the training distribution. What happens when the model encounters a molecule that looks nothing like anything it was trained on, and how confident we can be that the network's internal representations correspond to anything physically real? These are exactly the questions that the field of interpretable AI in physics is grappling with right now in 2025. There's something quietly profound in all of this that goes beyond the science. Pascal spent his entire life trying to measure things that people said could not be measured. The pressure of air that no one could see, the weight of nothing, the vacuum, the probability of outcomes that had not yet happened. He gave human beings instruments to read what had always been there but never been legible. Artificial intelligence, at its best, and in the hands of physicists who use it correctly, is doing the same thing. It is building instruments to read patterns in data that human cognition alone cannot process. Patterns in quantum systems, in climate models, in gravitational wave signals arriving from collisions a billion light years away. The LIGO collaboration, which detected gravitational waves for the first time in 2015, now uses deep learning models to distinguish genuine wave signals from instrumental noise in real time. They are using a trained network to hear the universe. Pascal climbed a mountain to read the air. We are now listening to the fabric of space-time with a neural network. The distance between those two acts is 3.5 centuries. The spirit behind them is identical. What this tells you, if you are someone who has ever felt that the world is more ordered than it appears, that there are patterns underneath the chaos you are living through, that the invisible forces pressing on your life are real, even if no one has given you the instruments to measure them yet, is that you are right. The instruments get built. They always get built. Pascal built his. The physicists of the 20th century built theirs. The AI researchers of this century are building theirs right now. And every instrument ever built to read the invisible world started with one person refusing to accept that the invisible was unmeasurable. That is the invitation Pascal's life extends to you today. Not to believe without evidence, but to build the instruments, run the experiment, and read whatever the universe is actually saying.